At the end of the last lecture, we jumped ahead to look at the consequences of Mendel's discoveries and Walter Sutton's interpretation of them that led to our modern idea of what Mendel's particles actually were. Now what I want to do is go back to Mendel's problem because it's time for us to get beyond the Punnett square sort of junior high way of looking at genetics and look at it in a more professional way, the way Mendel used and the way that we use today in the profession. It allows us to solve much more difficult problems and in fact is much easier to apply than a Punnett square. But the Punnett square is something that's good when you're first learning it. But here's the deal. Mendel dealt with more than just 2 traits at a time. He also looked at what would happen if you get 3 traits at a time. And in fact, using the techniques that he used, you could look at all 7 traits being passed down all at the same time without using a Punnett square. Now here's why you don't want to use a Punnett square. Suppose we have this problem. We want to know what are the expected phenotypes and phenotypic ratios from a cross where you have spherical, yellow, tall, purple plants. And they're all heterozygous, they're all F1s. So spherical is 1 trait, yellow is another trait, tall's and is a third, and purple is a 4th. Okay, so how many particles do we have to deal with when we're talking about the genotypes? Well, again, Mendel said there's 2 particles for every trait. There are 4 traits here. Therefore, there's got to be 8 of these particles we have to deal with. So we're talking about an F1. So they're heterozygous in all 4 of those traits. So here would be an example. Big A, big B, little b, big C, big D, little d. Now I'm using just A, B, C, D here because it's a little bit easier. But here we have spherical is A, yellow is B, tall is C, purple is D, or better, seed shape is A, seed color is B, the height of the plant is C, and the color of the flower is D. Okay, so how big would your Punnett square have to be in that case if you wanted to solve this with a Punnett square? On the first exam and on the final, you will see a problem that is essentially the same as this. Don't try to use a Punnett square. Just if you do, you're going to run out of time because that's the problem. How big would it have to be? Well, remember, to make the Punnett square, we have to lay out all the gametes, every single gamete that can be produced by this parent right here. And to do that, well, this parent can give 1 of each of these letters, A, B, C, D, to the offspring, but it has 2 different forms of the A's, B's, and C's, and D's. So there's 2 forms of A it can give, 2 forms of B. Therefore, the number of different combinations we can have for just A and B is 2 times 2. And we saw that before. There's 4. That's why when you're looking at just the dihybrid, you're looking at putting these together in that sort of way. We have 4 different gametes. But to this we have to add the possibility of 2 C's. So we have 2 times 2 times 2. So 2 times 2 is 4, 4 times 2 is 8. Times another 2 for D, which is 16. So if we're going to make our Punnett square, the Punnett square would have to be 16 by 16. You're going to have to fill in 256 cells. So that's what I'm saying. Don't do that on the exam. There's no way you're going to have time to do all of that. But there's a much, much better way to do it, which requires a little bit of probability theory. So we're going to introduce that. And that's one of the reasons why it is that we don't start there, because most students at this level don't have the probability theory under their belt. So we're going to just develop that a little bit. There's not a lot that we need. But first of all, we're dealing in probability with random events, and we know that a random event is any event in which you cannot predict with certainty what the outcome is going to be. We've seen that already. Okay, now your book talks about 2 different rules. They call it the multiplication rule and the addition rule. Really, the multiplication rule is the definition of independence, and the addition rule has to do with disjoint probabilities. But you can call it that. That's fine. But here's the first one. This is one of the most useful theorems, one of the most useful ideas in mathematical probability is this. Suppose you have 2 different random events, and I'm just going to call them A and B. I don't care what they are. There could be a coin flip would be A, a second coin flip would be B. Okay, it could be the weather today versus the weather tomorrow, whatever. But suppose that they're independent. The weather today and tomorrow wouldn't be, but the coin flips probably are. Now we'll talk about what independence means here in just a moment, but suppose A and B are 2 independent random events. So what we mean here is that whatever the outcome of A happens to be, it has no impact on what the outcome of B happens to be. So think about coin flips. If I flip a coin, on the first flip I get a heads, does that change the probability that I get a heads on the second flip? If it doesn't, then those flips are independent. If it does, then they're dependent. So assuming that they're independent, then the probability that both A and B occur together, I flip a coin and get a heads the first time, and then I flip a coin and get a heads the second time. That would be A and B together. What's the probability of that event? That would be written as this, PR of A and B, the probability of A and B occurring at the same time, if they're independent, is simply the probability of A times the probability of B. Now, we do this all the time. This is sort of a natural thing to do, and it's kind of intuitive, even though when you're actually dealing with it, it needs sometimes to be parsed out very, very carefully. But that is one of the most useful rules that we have in probability theory. So let's just apply it just to see how it works, okay? Let's actually use the example I was using. What's the probability that in 2 consecutive coin flips we get a heads both times? Now, let's assume that those coin flips are independent, as is reasonable, right? So the first thing, if you flip a coin the first time, doesn't really have much of an impact on what the second coin flip is going to be, especially if you're using a second coin that's independent of the first. It's not even the first coin itself. The first one's a penny, the second one's a nickel, for example. Okay, well, what's the probability that you get a heads on the first flip, assuming the coin is fair? We talked about this earlier. Fair coin, the probability of that is going to be 1/2, because we expect an infinite number of trials, half of them will eventually be heads and half will be tails. Okay, so what this is saying then is that the probability of the first event A is 1/2. The event B is a second coin flip. Its probability of heads is also 1/2. So therefore, what's the probability of getting 2 consecutive heads both times? Simply this is the probability of heads on the first flip times the probability of heads on the second flip. So it's very straightforward. Probability of heads on the first flip is 1/2. Probability of heads on the second flip is 1/2. We multiply them together, we get 1/4. So that means this: if you flip a coin 2 times, 1/4 of the time you should expect to get 2 heads. Okay, so that's the approach. Now, this can be used in all kinds of much more complicated ways to solve much more complicated problems. Let's talk about this. Joe and Amy are 2 people that want to have children. They plan to have 2 kids. What's the probability that the first child is a boy and the second child is a girl? Here we need to talk about assumptions. The assumptions that people make when they do these kinds of calculations. Now, when I ask this in class, I say, okay, what's the probability? Almost everybody comes on the same solution as this, because they say, well, this is just like tossing a coin on the first kid. The probability that it's a boy is 1/2. The probability of the second kid is a girl is 1/2. Yes, but you're making an assumption which is not true. The probability of a boy the first time is not 1/2 in the United States. Slightly more boys are born than girls. Therefore, the probability of a boy is slightly higher. So therefore, if we're looking at this, we'd have to use the statistics from that. The probability of a boy in the United States is about 51%. 51% of the boys, or sorry, 51% of children born in the United States are boys, and only 49% are girls. So we'd have to use that. So again, my point here is this: be careful of your assumptions. If you're making an assumption, try to identify the assumption you're making and test it to see if it's actually right. Okay, so in this case then, to get the correct answer, it's going to be close to 1/4, because the probability of the first kid as a boy is close to 1/2. It's 0.51. The probability of the second kid being a girl is, again, close to 1/2. It's 0.49. Now notice how I'm doing this. I'm not saying 51% times 49%. That's not the proper way to express a probability. I don't care if you do it when you're speaking and when you're saying things. That's fine. But when you're doing these kind of calculations, don't take 51 times 49. That's not the correct answer. The correct answer is 0.51 times 0.49, and we get something, of course, very, very close to 1/4, 0.2499. We can use the addition rule for more complicated problems as well. For example, suppose we're looking at a family of 5 children. If we have a family with 5 kids, what's the probability that all the children are girls? Now, the reason this is an interesting question is because a lot of times people will say things like, and they'll say this to me oftentimes, like, well, all my siblings are the same sex as I am. All my siblings are girls, so girls run in my family. Well, it's possible, isn't it, that you could have a family with 5 kids that'd all be girls just by chance. So what is the probability of that? Before you can say that my family tends to have girls, you would have to check to see if that's just random or if that's some reason that your mother produces girls or your father produces girls for some reason, usually be their father. Okay, so let's figure this out. So we know then, what's the probability that the first kid is a girl? Well, we know from this previous question that that probability is 0.49. But now we got 4 others that we have to deal with. So what we're saying is, what's the probability that the first kid is a girl and the second kid's a girl and the third and the fourth and the fifth, all girls? Okay, now notice this is the same thing as this. What's the probability that the first kid's a boy and the first kid's a girl? This becomes important. Okay, notice how I'm saying that, and. There's an and in here. Okay, so if that's a probability, then, well, what's probably the first two kids is simply 0.49 times 0.49 or 0.49 squared. The third kid would be true if, again, we're assuming that these are all independent. It turns out they're actually not, but it's close enough. So what's the probability that the third kid's a girl, given that the first two are girls? Well, we know that the probability of the first two are girls is 0.49 squared, so it's 0.49 squared times 0.49, which is 0.49 to the third power. And if we continue that sort of reasoning, we get ultimately 0.49 to the fifth power, one for each child. Okay, if you calculate that thing out, what you get then is 0.02825. Okay, now, this is important. Whenever you see a number like this, always ask yourself what the number actually means. If you want, you can put this down to a percentage, 2.825% or almost 3%. Okay, so it's nearly 3% of what are what. Okay, that's the question. 3% of families with 5 children would have all girls. That's what this number means. So when you're looking at the number, don't just look at the number. Think about what it means in those terms. 3%, approximately, slightly less than 3% of all families with 5 children are girls if having the sex of a child is independent. Okay, so that's the question. So this is going to become useful for us. What about this? What's the probability that if you have a family with 5 kids, what's the probability you have at least one boy? You can also use the same sort of thinking process to solve that problem. Now, there's 2 different ways you can do this. There's a ridiculously hard way to do it, and then there's a really, really easy way to do it. In science, scientists tend to be people who seek the easy way to do it but get the right answer. And what that requires you to do is get your head out of the box and look around at the problem from all different angles, and you can see it in that kind of light. Then you can often see a simpler solution than the obvious solution. The obvious way to approach this is to say, okay, well, let's calculate the probability of having a boy. Okay, well, let's say then probability of a boy is 0.51 and the other 4 are girls. So it'd be 0.51 times 0.49 to the 4th power. But that would not be correct, because that's assuming that the boy was first and the rest were girls. Now you have to take into account the probability that the boy was second, and then the probability the boy was third, and then the probability he was fourth, and then the probability he was fifth. But this also says at least one child, so it could be 2 boys. So the first 2 could be boys and the rest girls, or the first and the third could be boys and the rest girls, or the first and the fourth could be boys and the rest girls. Then you have to take into account the probability of having 3 boys and 2 girls, and then 4 boys and 1 girl, and then all 5 boys. That's a hard way. The easy way is this. We already just calculated what the probability is that all the kids are girls. Any other possible result must be at least 1 boy. So all we have to do is this. 100% of families with 5 kids are either all girls or have at least 1 boy. So 100% is 1. That's the probability. So what we do is we say this. We're going to subtract from that 1 all the families, the proportion of families that are all girls. And that's got to be then the proportion to have at least 1 boy. Okay, so the solution is simple. 1 minus 0.49 to the 5th power, which is 1 minus about 3, which is about 98% or 97%. Okay, so what does this say, that number right there? Approximately 97%, 0.97175, of what are what? Think that through. Okay, think that through carefully before I give you the answer. Okay, we'll come back to that. All right, now, there's another rule that's very, very important, and that's this thing your book calls the addition rule. The addition rule is different. It says, okay, suppose there's a random event that can occur in more than one way. Okay, suppose that there's a possible outcome that can occur in more than one way. Here's an example. We have a big A little a cross big A little a. What's the probability from that cross that you're going to get a heterozygote offspring? Well, remember, there's 2 different ways that can happen. You can get the big A from the first parent and the little a from the second, or you can get the little a from the first parent and the big A from the second. So there's 2 different ways that can happen. That's the same kind of idea. Now, suppose you have those 2 ways that outcome A can occur. I'll call them A sub 1 and A sub 2. Now, we're also going to assume that they're disjoint, meaning that they can't both occur at the same time. Okay, in this case, they're disjoint, the example that I gave, because you have to get one big A from either the first parent or the second parent, and there's nothing else that can overlap. Okay, so as long as they're disjoint, you can do this. Then the probability of the event A, the heterozygote, is simply the probability of the first event, the first way it can happen, which is, in this case, the big A came from the first parent, the little a from the second, plus, or the probability that you get the big A from the second parent and the little a from the first. Okay, so the probability of the event A, if it's disjoint, the two different ways can happen, is simply the probability of the first way it can happen plus the probability of the second way it can happen. Okay, now think about how this is being asked. What's the probability of A? Well, A can occur either this way or this way, right? So what's the probability of this way or this way? Notice, or equates to plus. And if we go back up here, we say, what's the probability that the first kid's a boy and the second kid's a girl, and equates to times? This is actually a fairly common generality in mathematics. This symbol here in logical mathematics often translates to the concept of or. And this symbol here in logical mathematics often translates to the concept of and. So times we're combining, but remember, you have to have the correct assumptions and you have to be doing it correctly. This and applies only if they're independent. This or plus applies only if they're disjoint. Okay, so in general then, we can use both of these to solve very complicated problems in a way which I'll show you here very shortly. So the best way to learn these kinds of things is to apply them and see how they work. So let's do that right now. The addition rule can be used to solve this problem. Joe and Amy, what we're going to do is ask what is the probability that in their family of two that they have one boy and one girl. Okay, now notice that's different than what we were asking before. The question that we asked before was the probability that Joe and Amy have a boy first and then a girl. So here we don't care the order. We're just simply asking what's the probability that they have a girl and then a boy. It doesn't matter which one comes first. Okay, now, if we think about this, there's three possibilities in these kinds of families. You can either have two girls, you can have a girl and a boy, and you can have a boy and a boy. Now, those are the three possibilities. So what's the probability of having this, one girl, one boy? Well, it isn't 1/3. And the reason it's not 1/3 is that the number of ways you can get this and this is different than the number of ways you can get this. If you think about it, just like we thought about it before, it actually makes sense. So if we put all of these together, we're asking what's the probability of having a girl and a boy or a boy and a girl? Because those are the two different ways that can happen. All right, so here are all the possible probabilities. The probability of having a girl and a girl is 0.49 squared, which is 0.2401. The probability of a girl and a boy is 49 times 0.51. The probability of a boy and a girl is just simply the reciprocal of that, not the reciprocal, but the opposite of that, 0.51 times 0.49, and the probability of a boy is 0.51 squared. Okay, now, the two highlighted ones are the two ways that you can end up with a family with a girl and a boy. And so there's two different ways that this can happen. It can happen this way or this way, and they're disjoint. There's no other way, there's no overlap that can occur here. And so the probability that Joe and Amy have a family with a boy and a girl is simply the addition 0.2499 plus 0.2499, which becomes this 0.4998. Okay? So 0.4998 is the probability that any family is going to have a boy and a girl if what they have then is two children. All right, now it's time to apply all that theory to the genetic problems that we've been trying to solve. And I want to start with one that we've already solved, and that's this. Suppose we are going to cross two spherical yellow-seeded F1s. Okay, now you know this. We've seen this before. So we're going to cross spherical yellow F1, and we're asking what's the probability that the offspring is spherical green? Okay, now, before you address this, just like any other genetics problem, we want to look at, first of all, can we see these traits as independent? And of course, as always, we're trying to figure out what are the genotypes of the parents. All right, now, eventually we're going to figure out these probabilities. What's the probability that the offspring is round or spherical? And what's the probability that the offspring is green? All right, so I want you to do that on your own. Pause the video, and let's actually go ahead and solve that, put it down on a piece of paper, and then come back to the next video and see what the answer is.